Hello friends, and welcome back to a quiet evening of science and story. I am so glad you have chosen to spend this peaceful stretch of time winding down with me, wherever you are in the world, whatever hour the clock shows, whether you are wrapped in blankets on a cold night, listening with your eyes already half closed, or simply letting the day's noise fade into the background. This is your time now. Take a slow breath, let your shoulders drop, let your jaw soften, and let yourself be carried gently into one of the strangest, most beautiful chapters in the history of our planet. Tonight, we are going to travel back roughly 234 million years to a time when the Earth looked nothing like it does today. There were no separate continents as we know them, no Atlantic Ocean, no Pacific shoreline as we would recognize it. Instead, every piece of land on the planet was fused together into one enormous supercontinent that scientists call Pangaea. And surrounding this vast block of land was a single, borderless ocean called Panthalassa, stretching from horizon to horizon in every direction, deeper and wider than anything the modern world can offer. But here is the part that makes tonight's story unlike anything we have explored before. We are travelling to the only time in Earth's history when the safest place to be was not on solid ground, not under the shade of a tree or inside the shelter of a cave, but deep beneath the surface of the water. For a span of nearly 2 million years, the land became a nightmare. Volcanoes choked the sky with poison, acid rain stripped the soil bare, lightning set fire to forests that were already drowning, and floods swept away entire ecosystems that had taken millions of years to build. Yet beneath the waves, something remarkable was happening. While the land was tearing itself apart, the ocean, despite its own suffering, remained a refuge. Marine reptiles that had been quietly thriving for millions of years continued to grow, to hunt, to flourish in waters that stayed more stable, more temperate, more forgiving than anything the surface could offer. This is the story of the Carnian pluvial episode, the time it rained for 2 million years, and the reason the deep water became the last safe place on Earth. But before the storms began, before the first volcanic crack split the ocean floor, the world was a very different place. Let us go there first, to the quiet before the chaos, and imagine what it felt like to stand on a planet where nothing seemed likely to change. Picture yourself standing somewhere near the centre of Pangaea. The ground beneath your feet is hard, cracked and bleached by a sun that has been baking this land for millions of years without interruption. The air shimmers with heat. There is no sound of running water, no rustle of thick forest canopy, no bird song, because birds do not yet exist. Instead, the silence is broken only by the occasional rasp of sieve scales against dry stone, or the distant call of a reptile echoing across a landscape so flat and barren that you can see the curve of the horizon. Deserts stretch in every direction, reaching farther than any modern desert on Earth. The Sahara, the Gobi, the Atacama, all of them together would be small patches compared to the interior of Pangaea. Rivers are rare enough to feel miraculous, thin ribbons of water that cut through the red rock before vanishing into sand. Forests exist, but they cling only to the coastlines and the banks of those scarce rivers, patches of green surrounded by an ocean of dust. The creatures that rule this world are built for drought. Rhynchosaurs, barrel-bodied herbivores with heavy-beaked jaws designed to shear through the toughest dry vegetation, roam across the plains in herds. They are among the most abundant land animals of this age, perfectly adapted to a life of heat and scarcity. Alongside them lumber Ditynodonts, strange tusked creatures that are not quite reptiles and not quite mammals, holdovers from an even older era, digging for roots in the hard ground with the patience of animals that have known nothing but drought. Above them in the food chain sit the archosaurs, a broad group of ruling reptiles that includes the ancestors of both crocodiles and birds. Some of these early archosaurs are formidable predators with sprawling gaits and heavy jaws, built for ambush in a world where prey moves slowly and predictably. They are the undisputed kings of the land, And then there are the dinosaurs. They exist at this point in history, but you would barely notice them. They are small, most of them no bigger than a large dog, and they make up less than 5% of all the land animals you would encounter. They dart through the undergrowth quick and nervous, staying out of the way of the larger creatures that dominate every ecosystem. If you were standing in that Triassic desert, you might watch one sprint past you, a lean and fragile-looking thing on thin legs, and think nothing of it. You would never guess that this insignificant creature's descendants would one day rule the entire planet. But now, let us shift our gaze. Let us leave the burning interior of Pangaea and walk toward the coast, toward the edge where land meets the vast Panthalassa Ocean. As the dry wind fades behind you and the sound of waves grows louder, a different world reveals itself. Beneath the surface of that ocean, life has been recovering at a pace that the land cannot match. It has been roughly 20 million years since the worst catastrophe in Earth's history, the Permian-Triassic mass extinction, which wiped out over 90% of all marine species. The land is still rebuilding, and still fragile, still dominated by survivors clinging to familiar patterns, but the ocean has pushed ahead. Marine ecosystems have reached a level of complexity that mirrors what we see in modern seas, with full food chains running from the tiny plankton all the way up to enormous apex predators. And the rulers of this underwater world are the ichthyosaurs. These are marine reptiles that evolved from land-dwelling ancestors who returned to the sea, much like the ancestors of modern dolphins and whales would do hundreds of millions of years later. By this point in the late Triassic, ichthyosaurs have diversified into dozens of species. Some are small and agile, hunting fish in shallow coastal waters. Others are enormous. Shonisaurus, whose fossils have been found in what is now Nevada, stretches 15 meters from snout to tail, a sleek and commanding predator gliding through deep water with the ease of a creature perfectly adapted to its world. These animals are not struggling, they are thriving, and they will continue to thrive through the catastrophe that is about to engulf the land, because the water will protect them in ways the surface cannot. But we are getting ahead of ourselves. For now, the ocean is calm, the land is dry, and the world seems locked in a pattern that could last forever. It will not. Deep beneath the floor of the Panthalassa Ocean, far from any coastline, far from any creature's awareness, something is stirring. Hundreds of kilometers below the surface, a plume of superheated rock is rising through the Earth's mantle. It moves with the patience of geology, inches per year, but with a force that nothing on the surface can resist. And this rising column of magma is pushing against the ocean floor, building pressure across an area so vast that it stretches from what we now call Alaska, down through British Columbia and beyond. Scientists have given this volcanic system a name. They call it the Wrangellia Large Igneous Province, and when it finally breaks through the ocean floor, it will unleash one of the largest volcanic events in Earth's history. Not a single eruption, not a single mountain blowing its top, but an entire region of the planet's crust, splitting open and pouring molten rock into the sea for hundreds of thousands of years. The scale is almost impossible to imagine. Over the course of roughly 1.6 million years, the Wrangellia eruptions will release more than 1 million cubic kilometers of basaltic lava. To put that into perspective, and the eruption of Mount St. Helens in 1980 produced about 1 cubic kilometer of material and was considered catastrophic. Wrangellia produced 1 million times that amount. Rivers of glowing orange rock flowed across the ocean floor, building new layers of crust, boiling the water above them and sending columns of superheated gas and steam rocketing into the atmosphere. But the lava itself was not the real danger. The true weapon of these eruptions was invisible. With every pulse of volcanic activity, Wrangellia pumped staggering quantities of carbon dioxide, sulfur dioxide, and methane into the atmosphere. These gases rose through the ocean, broke through the surface, and drifted into the sky, where they began to wrap the planet in a thickening blanket of heat. Carbon dioxide trapped the sun's warmth preventing it from escaping back into space. Global temperatures began to climb, not by a degree or two, but by 4 to 8 degrees Celsius across the entire planet. That might not sound dramatic if you are thinking about the difference between a warm day and a slightly warmer one, but on a planetary scale, a shift of 4 to 8 degrees is the difference between a world with ice caps and a world without them. It is the difference between predictable weather and chaos. The warming did something else, something that would prove far more destructive than the heat itself. As temperatures rose, evaporation from the Pan-Thalassa Ocean accelerated. More water vapour lifted into the atmosphere than the sky had held in millions of years. Pangaea, that enormous landmass, already created intense monsoon patterns simply because of its size. See, hot air rising over the interior pulled moist ocean air inland, generating seasonal rains along the coasts. But now those monsoons were being supercharged by volcanic heat. The moisture in the atmosphere was not just increasing, it was multiplying, building into cloud systems of a size and intensity that the Triassic world had never experienced. The eruptions did not happen all at once. Research published in the Proceedings of the National Academy of Sciences has shown that the Wrangellia eruptions came in 4 distinct pulses, each one separated by a period of relative quiet, each one marked by a sharp spike in mercury levels preserved in ancient lake sediments from China. These mercury spikes are the fingerprints of volcanic activity, carried by the wind across the globe and deposited in the mud of distant lakes. 4 pulses, 4 surges of gas into the atmosphere, 4 waves of warming that each pushed the climate further from the stability that life depended on. And with each pulse, the clouds grew darker, the monsoons grew fiercer. The moisture that had been building in the atmosphere reached a tipping point, and the sky, which had been clear and dry for millions of years over the interior of Pangaea, began to change colour. Grey clouds crept across the horizon. The air grew heavier, wetter, carrying a strange new scent that no creature on this dry continent had ever known. Then the first drops fell. At first the rain might have seemed like a gift to a parched world. Imagine those initial drops hitting the cracked red earth, each one evaporating almost instantly against the heat of the ground. Imagine the dust rising in the tiny puffs where water met soil for the first time in ages. For the creatures that had survived on scarcity, that first rainfall must have been a curiosity, perhaps even a relief. But this was not a passing shower. This was not a season of unusual weather. This was the beginning of something that would last for nearly 2 million years. The clouds did not part, the rain did not stop, and the world that had been locked in drought for as long as any living thing could remember was about to discover what happens when the sky itself turns against the land. What followed would be the most sustained period of rainfall in Earth's known history. Scientists call it the Carnian Pluvial Episode, and its effects would ripple through every ecosystem on the planet, drowning some, transforming others, and opening doors that would change the course of evolution forever. The land was about to become a place of unimaginable suffering. The ocean, tested but enduring, was about to become the last sanctuary on Earth. And it all began with the rain. The rain did not arrive gently and then leave. It arrived gently and then stayed. What began as scattered showers across the coastlines of Pangaea deepened into something relentless, something the Earth had not experienced in living memory, something that would not stop for nearly 2 million years. To understand how completely the land was transformed, you have to remember what it looked like before. The interior of Pangaea was a desert continent, its surface baked hard under millions of years of unbroken sun. Rivers were thin and seasonal, forests were rare. It confined to the edges of those rivers and the narrow margins where land met the sea. The soil itself was compacted and dry, resistant to erosion, holding its shape like sun-baked clay. Now imagine all of that dissolving. The first weeks of sustained rain softened the surface. The cracked red earth absorbed what it could, but the soil had been dry for so long that it could not hold the water fast enough. Puddles formed, then pools, then shallow lakes where none had existed before. The rivers, those thin ribbons that creatures had depended on for generations, began to swell. Their banks, weakened by the sudden saturation, crumbled and gave way. Water spilled across the plains in broad flat sheets, turning familiar paths into impassable marshes, within what geologists estimate to be just a few thousand years. So the transformation was visible in the rock record. One layer of sediment shows a desert landscape. The next reveals floodplains alive with moisture. The shift was so abrupt that when scientists first noticed it, they were unsure what could have caused such a dramatic change. In the 1970s, geologists Wolfgang Schlager and August Schollenberger were studying the northern limestone Alps of Austria when they discovered something unexpected. Nestled between millions of years of dry carbonate rock, there was a thin, dark layer of silicic sediment, the kind of rock that only forms under intensely wet conditions. It was as if someone had drawn a line through the geological record and written the word rain across it. Later investigations revealed the same layer in England, in Israel, in Italy, and in the United States. And this was not a local flood. This was a global event. The evidence kept building. In the Italian Dolomites, researchers found something even more striking. Beneath the reddish mudstone layers that mark the beginning of the Carnian pluvial episode, there are no dinosaur footprints, none at all. But directly above those same layers, dinosaur tracks appear in abundance. That sharp boundary in the rock tells us that the world changed so dramatically during this period that entirely different creatures walked the land afterward. The old rulers vanished, new ones took their place, and the dividing line between those two worlds is a layer of mud left behind by rain that would not stop. For the creatures living through it, the change was catastrophic. Rhynchosaurs, those barrel-bodied herbivores with their heavy beaks, that would thrive for millions of years by feeding on the tough, dry vegetation of Pangaea's interior. Their jaws were perfectly designed to shear through fibrous plants that grew in arid soil. But when the rains came and those plants drowned, when the ground softened and new moisture-loving ferns and conifers began to replace the old vegetation, the rhynchosaurs had nothing left to eat. Their jaws, once their greatest strength, became useless against the softer, wetter plants that now carpeted the land. The fossil record shows their decline was swift. Within the span of the Carnian, they were gone, an entire lineage of successful animals erased because the world they were built for simply ceased to exist. Dicynodonts suffered a similar fate. These tusked, heavily built creatures had been among the largest herbivores on land, the survivors of the Permian-Triassic extinction that had wiped out most of life on Earth just 20 million years earlier. They had endured the worst catastrophe in the planet's history, only to be brought down by rain. Their massive bodies, so well suited to digging through hard ground, became a liability in the soft waterlogged terrain. They sank in mud. Their nesting grounds flooded. Their food sources shifted beneath them. But the rain was only one part of the nightmare. The same volcanic eruptions that drove the rainfall also poisoned the atmosphere. With each pulse of the Wrangellia eruptions, sulfur dioxide and carbon dioxide flooded the sky. When these gases mixed with the moisture in the atmosphere, the rain that fell was not pure water. It was weak acid, carrying dissolved sulfur compounds that stripped nutrients from the soil, and killed freshwater organisms, and turned ponds and streams into hostile environments where amphibian eggs could not survive. Imagine a swamp alive with the croaking of early amphibians, their eggs clinging to the stems of water plants, their tadpoles swimming in the shallows. Now imagine that same swamp after years of acidic rainfall, its water clouded, its vegetation yellowed and limp, its once vibrant life reduced to silence. That was the reality across much of Pangaea. And then there was fire. This is the part that seems contradictory, almost impossible. How could there be fire in a world that was drowning? But the storms that rolled endlessly across the land were electric storms, supercharged by the volcanic heat and the massive amounts of moisture in the atmosphere. Lightning struck with extraordinary frequency, and during the brief intervals between downpours, when the rain paused long enough for vegetation to dry even slightly, those lightning strikes set the land ablaze. Charcoal layers preserved in ancient soil confirm that wildfires were widespread during the Carnian pluvial episode. The land was caught in a cycle of extremes, burning and flooding in alternation, each swing pushing life closer to the edge. Picture this world for a moment. The sky is dark, perpetually overcast, pressing its weight down on the land. Rain falls in sheets, hammering the mud, swelling the rivers until they burst. Lightning cracks across the clouds, sometimes splitting trees, sometimes igniting patches of vegetation that burn fiercely until the next downpour drowns the flames. The air is thick with humidity, heavy with the faint smell of sulphur, and the ground squelches underfoot, unstable, treacherous. Creatures that once roamed confidently across dry plains now wade through knee-deep water, searching for ground that no longer exists. There is nowhere to go. There is no dry refuge. There is no high ground that stays dry for long. The rain follows everything, everywhere, without pause and without mercy. Now imagine being a small animal in this world, a creature that depends on hearing to detect predators. The roar of constant rain drowns out every subtle sound. You cannot hear the approach of a hunter. You cannot hear the call of your own kind. Sleep is shallow and broken, each clap of thunder jolting you awake. Stress builds across generations, weakening immune systems, reducing reproduction rates, thinning populations that were already fragile, and the land has become a prison with no walls, only water. This was the world above the surface for nearly 2 million years. Fire and flood, acid and lightning, collapsing food chains and vanishing habitats. The ground itself, the one thing that every land creature depends on for stability, had betrayed them. But there was another world, a world just beyond the coastline, just beneath the crashing waves, where the rules were different. Let us go there now. Imagine leaving that flooded, burning, thunder-shaken land behind. Imagine walking toward the shore, through the mud and the rain, until the ground slopes downward and the water rises past your ankles, past your waist, past your shoulders. Imagine the noise of the storm growing muffled as the water closes over your head. And then imagine the silence. Not perfect silence. And the ocean has its own sounds. The creak of shifting currents, the distant rumble of underwater geology, the faint clicks and hums of living things moving through the dark. But compared to the ceaseless roar of the surface, the ocean during the Carnian pluvial episode was a world of relative calm. Lightning could not reach you here, acid rain could not burn your skin, and wildfire could not chase you through the undergrowth. The water itself acted as a buffer, absorbing the shocks that were tearing the land apart and smoothing them into something livable. This is the heart of tonight's story. During the Carnian pluvial episode, the ocean became the safest place on Earth. Not safe in an absolute sense, because the sea had its own trials and we will come to those, but safer. Measurably, demonstrably, and geologically safer than the nightmare unfolding on the surface. The reasons for this are rooted in physics as much as biology. Water has an extraordinary capacity to absorb and distribute heat. While the land whipsawed between scorching volcanic warming and brief cooling episodes caused by sulphur aerosols reflecting sunlight, the deep ocean maintained far more stable temperatures. A creature living 50 meters below the surface of the Panthalassa Ocean would have experienced temperature changes so gradual, so muted compared to the chaos above, that for all practical purposes its thermal world remained constant. On land, a temperature swing of 8 degrees Celsius over the course of the Carnian could mean the difference between a functioning ecosystem and a collapsed one. In the deep ocean, and that same swing was absorbed across such a massive volume of water that its effects were softened to a fraction of what land creatures experienced. There was no acid rain underwater. The rain fell on the surface, and some of that acidity did seep into the shallow coastal waters, but the vast majority of the ocean, The open waters and the deep currents maintained a chemistry that marine life could endure. The volcanic gases that made the air toxic on land were diluted across an ocean so large that it covered more than 70% of the planet's surface, and there was no fire. Not a single bolt of lightning, not a single spark of flame could reach the creatures swimming in the darkness below. The food chains in the ocean were stressed, certainly, and we will talk about the algal blooms and the oxygen crashes that hit some marine ecosystems hard. But the fundamental structure of ocean life, the connection between sunlight and plankton and fish and predators, remained functional throughout the Carnian pluvial episode in a way that land food chains did not. On land, the base of the food chain, the plants, was being destroyed by a combination of flooding, acid rain, and fire. In the ocean, plankton continued to photosynthesize, continued to reproduce, continued to feed the fish that fed the larger predators. The system bent under pressure, but it did not break, and the proof of this is written in the fossils. During the late Triassic, ichthyosaurs reached the peak of their size and diversity. These were not creatures hanging on by a thread. They were expanding, growing larger, and filling new ecological niches with the confidence of apex predators in a stable world. Shonosaurus, found in Carnian age rocks in Nevada, was 15 meters long, a sleek 15-meter hunter that would have been among the most formidable creatures in any ocean in any era. Other shastosaurs from this period grew even larger, with some specimens exceeding 20 meters, making them among the largest marine reptiles that have ever lived. Think about what that means. At the exact same time that land creatures were dying in droves, unable to cope with the floods and the fires and the poisoned air, the ocean's top predators were reaching sizes that they had never reached before and would not reach again for millions of years. The land was in collapse. The ocean was building its largest, most successful predators, and the contrast could not be more stark. Research published in the Proceedings of the National Academy of Sciences has shown that the recovery of marine ecosystems after the Permian-Triassic mass extinction outpaced the recovery on land. Marine food webs reached modern levels of complexity, complete with apex predators capable of hunting prey as large as themselves, while the land was still rebuilding. The Carnian pluvial episode made this gap even wider. The ocean's head start in recovery gave it a resilience that the land simply could not match when the volcanic storms began. But the ocean's role during the Carnian pluvial episode was not just about survival, it was about creation. The CPE marks the first appearance of modern coral reefs, built by scleractinian corals, and the same group that builds the Great Barrier Reef and every other coral reef on Earth today. Before this period, the ocean floor was shaped by different organisms, older reef builders that could not survive the changes in ocean chemistry that the volcanic gases brought. But scleractinian corals could. They appeared during the Carnian, established symbiotic relationships with algae called zooxanthellae, and began constructing the reef systems that would become the most biodiverse habitats in the ocean for the next 230 million years. At the same time, the microplankton of the ocean underwent a revolution. Coccoliths, tiny calcium carbonate plates produced by single-celled algae called Coccolithophores, made their first appearance in the fossil record during the Carnian pluvial episode. So did Dinoflagellates, another group of microorganisms that would become essential to marine food chains. These organisms are not just ancient curiosities, they are the foundation of the modern ocean, the plankton that float in the seas today, that produce roughly half the oxygen we breathe, that form the base of every marine food chain on the planet, trace their origins to this period. The storm that devastated the land gave birth to the modern ocean. Imagine that contrast one more time. Above the surface, the sky is black with storm clouds. Rain hammers the mud. Lightning splits the air. Fires burn on distant hillsides, their smoke mixing with the sulphurous haze. Creatures wander through the wreckage of ecosystems that have been destroyed, starving, lost, their populations crashing toward extinction. And below the waves, in the cool, dark water, an ichthyosaur, glides forward through currents that have barely changed temperature in 1,000 years. Around it, plankton drift in clouds of green and gold. Small fish dart between the shadows. A coral reef, one of the first of its kind, is slowly building itself on a rocky shelf, each tiny polyp adding another grain of limestone to a structure that will endure for millennia. The land is screaming. The ocean is breathing. For nearly 2 million years, this was the reality of life on Earth. The ground was treacherous, volatile, poisoned. The water was steady, deep, and patient, and the creatures that lived beneath the waves carried the spark of life forward through a storm that the land could not survive. Let us stay beneath the waves a little longer, because the world down here is worth knowing. You close your eyes and imagine sinking slowly through the water column of the Panthalassa Ocean, 234 million years ago. The light from the surface, already dimmed by the perpetual storm clouds above, fades as you descend. The water shifts from grey-green to deep blue, and then to something close to black. The temperature drops gradually, a few degrees at a time, until it settles into a steady coolness that will not change for months or years. This is the world where the survivors lived, and the creatures you would meet here are among the most remarkable animals that have ever existed on our planet. The ichthyosaurs deserve more of our attention, because they are central to understanding why the ocean was safer than the land. By the time the Carnian pluvial episode began, ichthyosaurs had already been evolving for roughly 15 million years. They descended from land-dwelling reptiles that returned to the sea during the early Triassic, in a transformation that mirrors the much later evolution of whales from their terrestrial ancestors. Over those millions of years, their bodies had been reshaped by natural selection into something that looked remarkably like a modern dolphin. A torpedo-shaped body, broad flippers, a crescent-shaped tail, and large forward-facing eyes adapted for hunting in dim water. But the ichthyosaurs of the late Triassic were not all built the same. By the Carnian, they had diversified into an astonishing range of forms. Some were small and agile, no longer than a metre or two, darting through coral rubble and kelp-like algae in search of small fish and shrimp. Others were mid-sized generalists, hunting in open water at moderate depths. And then there were the giants. Shonisaurus, whose fossils were first discovered in what is now Nevada, was a creature that stretched 15 metres from the tip of its narrow snout to the end of its muscular tail. When paleontologist John Merriam led the Saurian expedition to central Nevada in 1905, financed by Annie Alexander, his team uncovered 25 specimens of these enormous marine reptiles, their bones preserved in rock that had once been the floor of a shallow Triassic sea. Some of those specimens are still embedded in the stone, visible today at Berlin Ichthyosaur State Park, silent witnesses to an ocean that thrived like while the land burned. But Shonisaurus was not even the largest of its kind. Other Shastosaurs from the late Triassic period grew to more than 20 metres in length. In 1992, paleontologist Elizabeth Nichols uncovered a specimen in the Pardonet Formation of British Columbia that measured an estimated 21 metres, one of the largest marine reptiles ever discovered. These were not desperate survivors clinging to the edges of a collapsing ecosystem. These were apex predators at the height of their evolutionary success, growing to sizes that spoke of abundant food, stable environments and thriving populations. The ocean was not merely keeping them alive, it was allowing them to flourish. Their success during this period tells us something important about the difference between land and sea during the Carnian pluvial episode. On land, the top predators were in decline, and large archosaurs that had ruled the floodplains were losing their prey base as herbivores starved and ecosystems collapsed. Fossilized bones of these land predators show the telltale signs of malnourishment, thin fragile structures that speak of prolonged hunger. Their world was shrinking around them. In the ocean the opposite was happening. The ichthyosaurs were not just surviving, they were diversifying, occupying new ecological niches, evolving new body plans and reaching sizes that they had never achieved before. This is exactly what you would expect in an environment that remained relatively stable while the world around it fell apart. The ocean was a refuge, and the creatures within it responded the way life always responds to safety and abundance. They grew. Alongside the ichthyosaurs, and other marine and semi-aquatic creatures found opportunity in the Carnian world. Phytosaurs, long-snouted predators that looked strikingly like modern crocodiles but were only distantly related to them, thrived along the expanding waterways of Pangaea. Their nostrils were positioned near the tops of their skulls rather than at the tips of their snouts, an adaptation that allowed them to lie almost completely submerged, with only their eyes and nose above the waterline, waiting for prey to wander close. As rivers widened and swamps spread across former deserts, the phytosaurs' hunting grounds expanded enormously. The same floods that drowned the land herbivores created a paradise for these semi-aquatic ambush hunters. Giant amphibians, the temnospondyls, also found their kingdom expanding. These were not the small, delicate frogs and salamanders of the modern world. Some temnospondyls of the late Triassic were massive creatures stretching 2 meters or more in length, with broad flat heads and jaws lined with rows of sharp teeth. They had been confined to dwindling pools and seasonal wetlands during the dry ages of the early Triassic. But when the rains came and the swamps spread, these ancient amphibians surged outward, reclaiming territory that drought had stolen from them millions of years earlier. Their moist, permeable skin, once a vulnerability in the dry heat, became a perfect adaptation for a world that was now saturated with water. Imagine the swamps of Carnian Pangaea at dusk. The rain is falling as it always is, a steady drumming on the surface of dark, still water. Beneath the surface, a temnospondyle lies motionless, on its body hidden in the mud, only its eyes breaking the waterline. A small reptile approaches the edge of the pool to drink, unaware of the predator below. The water explodes in a surge of teeth and muscle, and in an instant the prey is gone, dragged beneath the surface by a creature that was built for this exact moment. The swamp is deadly, but it is alive, thriving in a way that the dry land around it cannot match. Even the insects of this period tell the story of water's dominance. Dragonflies, their wings as wide as a man's hand, patrolled the humid air above the swamps, hunting smaller insects that swarmed in clouds above the standing water. Beetles chewed through the sodden bark of fallen trees. Aquatic insects of all kinds multiplied in the expanding network of ponds, rivers and marshes that now covered much of Pangaea. For creatures that depended on water, the Carnian pluvial episode was not a catastrophe. It was a golden age. There is one more piece of evidence that speaks to the ocean's role as a sanctuary during this period, and it comes from the most unexpected of sources. In the South China Block, a region that was covered by shallow seas during the Carnian, scientists have found a series of fossil-rich rock formations called Lagerstätten. These are deposits where conditions were so perfect for preservation that the fossils they contain are extraordinarily detailed, showing not just bones, but sometimes the outlines of soft tissues, stomach contents, and even the positions in which animals died. The reason these Lagerstätten exist is because the waters in which they form were low in oxygen, which prevented scavengers from disturbing the remains, and the creatures that settled to the bottom after death were left undisturbed, slowly buried in fine sediment, their forms preserved with a clarity that borders on the miraculous. The irony is profound. The same low oxygen conditions that made parts of the ocean dangerous for living creatures also created the conditions for their stories to be preserved in perfect detail. The mud that suffocated some creatures in life became the amber that kept their memory frozen in death. Ichthyosaurs, crinoids, and other marine animals from the Carnian are preserved in these formations with exquisite precision, their fossils telling us exactly what the ocean looked like during the years of endless rain. But now we must be honest, because the ocean story during the Carnian pluvial episode is not a simple tale of paradise beneath the waves, and the sea had its own trials, its own moments of crisis, and to understand why water was safer than land, we need to understand both sides of the story. the endless rains did not only fall on the land, they also flowed into the sea. Rivers that had once been thin seasonal streams now roared with unchecked fury, carrying enormous loads of soil, minerals, organic debris, and dissolved gases into the coastal waters of Panthalassa. This flood of nutrients changed the chemistry of the ocean in ways that were, at times, devastating. The first effect was the algae blooms. When rivers dump large quantities of nitrogen and phosphorus into coastal waters, it is like pouring fertilizer into a garden. Algae, those microscopic plants that form the base of the marine food chain, respond explosively. Great green and brown blooms spread across the surface of the Carnian seas, painting the water in swirls of colour that, from above, might have looked almost beautiful. But beauty masked a deadly truth. When algae multiply too quickly, they block the sunlight that deeper organisms need to survive. Fish and other creatures that depend on clear water find themselves living in a twilight zone, unable to see, unable to hunt, unable to find their way. And when the blooms eventually die, as they always do, their decomposing bodies sink to the bottom and are consumed by bacteria. Those bacteria use oxygen as fuel, and in their frenzy of feeding they strip the surrounding water of breathable air. This is the process that scientists call anoxia, the suffocation of the sea. During the Carnian pluvial episode, anoxia struck coastal waters and some deeper ocean basins with terrible force. In the South China Block, the geological record shows layers of black shale, a type of rock that forms only in oxygen-depleted water. These black shales contain evidence not just of low oxygen but of something even worse, a condition called euxinia, in which hydrogen sulfide, a gas that is toxic to virtually all animal life, accumulates in the water. Manganese ions enriched in the limestone near the top of the Jugunpo Formation tell scientists that the deeper waters in this region had become not merely lifeless, but actively poisonous. The scale of marine extinctions during the Carnian was real and significant. Roughly 33% of all marine genera disappeared during this period. Ammonoids, the spiral-shelled relatives of modern nautiluses, suffered major losses. Conodonts, small eel-like marine vertebrates whose tooth-like fossils are among the most useful tools for dating ancient rocks, declined sharply in both diversity and body size. Crinoids, the graceful flower-like animals that had been a mainstay of marine ecosystems for hundreds of millions of years, were devastated. Bryozoans, tiny colonial animals that formed reef-like structures on the seafloor, experienced species-level extinction rates as high as 85%. Marine bony fish lost between 51 and 62% of their genera. These are not small numbers. These are the signatures of a genuine marine crisis. The ocean was not untouched by the Carnian pluvial episode. It suffered. It lost species that had been part of its fabric for millions of years. And entire branches of the tree of life were pruned away by the changes in water chemistry, the loss of oxygen, and the flooding of coastal habitats with sediment and toxins. But here is the crucial distinction, the thread that runs through this entire story. The ocean recovered faster than the land. The marine extinctions, while severe, were followed by an explosive diversification of new species. Scleractinian corals appeared and began building the first modern reefs. Coccolithophores and dinoflagellates emerged among the plankton, establishing the base of food chains that still function today. New species of ammonoids evolved to fill the niches left by those that had vanished. The ocean bent under the weight of the Carnian crisis, but it did not break. On land, the story was different. The extinctions were not followed by rapid recovery. The creatures that vanished, the rhynchosaurs, the large dicynodonts, many families of archosaurs, left gaps that took millions of years to fill. The ecosystems that had existed before the rain simply did not come back. They were replaced by entirely new communities of plants and animals, dominated by survivors that bore little resemblance to the old world. The ocean was not safe, but it was safer. And in the arithmetic of survival, That difference was everything. The water absorbed the shocks that shattered the land. It buffered the temperature swings, diluted the toxins, and maintained food chains that allowed its inhabitants to endure, adapt, and eventually thrive in a world remade by fire and rain. While entire lineages of land creatures were vanishing into the fossil record, never to return, the ocean's residents were adjusting and shifting, finding new ways to live in water that, though changed, were still livable. The contrast between the two worlds grew sharper with each passing century. On the shore, death; in the depths, persistence. And so, as the storms raged on above, as the land continued to drown and burn and poison itself, under the relentless assault of volcanic gases and acid rain, the creatures of the deep continued their ancient rhythms. Ichthyosaurs hunted in the darkness, plankton drifted in the currents. Corals, the first of their modern kind, built their patient structures on the ocean floor. Life beneath the waves was not easy, but it was possible, and for nearly 2 million years that was more than the land could say. While the ocean carried its largest inhabitants through the storm with something resembling grace, while the land was engaged in a far more brutal sorting, the rain did not care which creatures were strong or which were ancient. It did not respect the millions of years that Runningosaurs had spent perfecting their beak jaws, or the generations that Dicynodonts had invested in their tunneling skills. The rain simply fell, and everything that could not adapt to its falling was washed away, but not everything perished. In the wreckage of the old world, certain creatures found something unexpected. They found opportunity. Before the Carnian pluvial episode, dinosaurs were among the least important animals on land. When paleontologists count the fossil specimens from pre-Carnian rock formations, dinosaurs make up less than 5% of all the land vertebrates found. They were small, most of them no larger than a medium-sized dog, and they were fast, with long thin legs held straight beneath their bodies in an upright posture, unlike the sprawling stance of most other reptiles. But speed and small size were not enough to win them dominance in a world already claimed by much larger, more established competitors. Before the rains, dinosaurs were the background players of the Triassic, darting through the undergrowth, snatching insects, avoiding the heavy footsteps of the true rulers overhead. The storms changed everything. When the rain turned the hard-packed deserts of Pangaea into swamps and the familiar ecosystems collapsed under the weight of water, the qualities that had made dinosaurs insignificant and suddenly became invaluable. Their upright posture, with legs held directly beneath their hips rather than splayed to the sides, had meant their bodies were lifted higher above the mud. While heavy, sprawling reptiles sank into the soft ground and struggled to move forward, dinosaurs could walk, and even run, across terrain that swallowed their larger rivals whole. Fossilized trackways from this period tell the story in vivid detail, deep dragging imprints from heavy animals fighting the mud alongside the lighter, more confident tracks of creatures that could still move freely. Their small size, once a disadvantage in a world where bigger meant safer, became protection in a world where everything was in flux. Small animals need less food. They can hide in tighter spaces. They can survive on a wider variety of diets, switching from insects to small amphibians to tender new plants as the landscape shifts around them. And the dinosaurs were generalists in a world that was punishing specialists, and that generalism saved them. Their lungs may have given them another edge. Modern birds, the direct descendants of dinosaurs, have a highly efficient respiratory system that uses air sacs to maintain a continuous flow of oxygen through the lungs, far more effective than the tidal breathing of mammals or typical reptiles. If early dinosaurs possessed even a primitive version of this system, they would have been better equipped to function in an atmosphere that was increasingly loaded with carbon dioxide from the Wrangellia eruptions. While other creatures gasped in the heavy, CO2-rich air, dinosaurs may have been able to extract enough oxygen to maintain their active lifestyles. And the evidence for the dinosaurs' rise is written in the same rocks that record the Carnian pluvial episode. In the Italian Dolomites, below the mudstone layers that mark the onset of the CPE, dinosaur footprints are entirely absent. The land was dominated by other creatures, archosaurs and rhynchosaurs and amphibians, that had held those ecosystems for millions of years. But directly above those mudstone layers, in the rock that was deposited after the rains intensified, dinosaur tracks appear in abundance. The transition is so sharp that paleontologist Mike Benton and his colleagues have described it as evidence of a strict relationship between the Carnian pluvial episode and the rise of dinosaurs. The storms did not just clear the stage, they handed the spotlight to an entirely new cast of performers. And it was not only dinosaurs that stepped into the gaps left by the old world's collapse. The Carnian pluvial episode also saw the diversification of crocodilomorphs, the ancestors of modern crocodiles, which adapted beautifully to the expanding network of rivers and wetlands. Turtles appeared, their protective shells an innovation that would carry them through every extinction. Events from this point forward. Lepidosaurs, the group that includes all modern lizards and snakes, achieved a worldwide distribution by the end of the Carnian. And perhaps most quietly, most consequentially of all, the first mammalia forms, tiny insect-eating creatures that were the distant ancestors of every mammal alive today, including us, also diversified during this period. The Carnian pluvial episode was not simply a catastrophe, it was a reshuffling, a forced clearing of the ecological deck that made room for entirely new ways of living. The old rulers were gone. The new ones were small, fast, adaptable and flexible, exactly the qualities that a chaotic, unpredictable world demanded. The plant kingdom underwent its own transformation. Before the rains, the vegetation of Pangaea's interior was sparse, drought-adapted, and dominated by plants that could tolerate extreme heat and scarcity of water. When the monsoons arrived, these plants drowned. Their roots, spread wide to scrape every last drop of moisture from the soil, were overwhelmed by the sudden abundance of water. Seeds rotted before they could germinate. Forests that had clung to the edges of seasonal rivers collapsed as those rivers burst their banks and spread across the landscape. But in their place, new plants surged forward. Ferns were the first to capitalize on the wet world. Their spores, which need moisture to germinate, had been limited to small pockets of habitat during the dry ages. Now, with water everywhere, they exploded across the land. Fossil pollen records from the Carnian show a dramatic spike in fern spores, a signal so distinctive that paleobotanists use it as a marker for the CPE itself. Where once the landscape had been brown and red with bare rock and sand, it was now painted in every shade of green. Behind the ferns came the conifers. These were the ancestors of modern pines, cedars and spruces, and they were built for endurance. Their trunks thickened in the softened ground. Their roots drove deep, gripping the damp earth, and their needle-like leaves were resistant to both the heavy rainfall and the acidic chemistry of the water. Generation by generation, the conifers grew taller, their crowns forming canopies that would eventually become the first great forests of the post-CPE world. This transformation of the plant kingdom had a cascading effect on everything else. New plants meant new food sources for herbivores. New forests meant new habitats for insects, which meant new food for small predators, which meant a richer ecosystem from bottom to top. The Carnian pluvial episode ended the early and middle Triassic coal gap, a period of roughly 15 million years in which peat swamps had been virtually absent from the planet. With the return of the rains, swamps reappeared, and with them came the conditions for coal formation, a signal that biological productivity on land was finally recovering from the devastation of the Permian-Triassic extinction 20 million years earlier. The lesson hidden in all of this is deceptively simple. The species that survived the Carnian pluvial episode were not the strongest. They were the most flexible. The rhynchosaurs were strong with their heavy beaks and their herds that had roamed Pangaea for millions of years, but they could not change. The Decinodonts were resilient, survivors of the worst extinction event in Earth's history. but they could not adapt fast enough to a world that changed faster than their biology allowed. The creatures that made it through the 2 million years of rain were the ones that could eat different foods when the old foods disappeared, live in different habitats when the old habitats flooded, and adjust their behaviour when the old rules stopped working. Adaptability, not strength, was the currency of survival, and that lesson is as true today as it was 232 million years ago. Now, you might be wondering how we know all of this. How can scientists be so confident about events that happened more than 230 million years ago, long before any human being existed, long before anything resembling a written record? The answer lies in the rocks, and the story of how scientists read those rocks is, in its own quiet way, as remarkable as the Carnian pluvial episode itself. The Earth keeps its history in layers. Every year, every century, every epoch leaves behind a thin film of sediment, whether that sediment is sand blown by desert winds, mud deposited by a river, shells accumulated on a seabed, or ash drifted down from a volcanic eruption. Over millions of years, these layers are compressed into stone, stacked on top of one another like the pages of an unimaginably long book. And if you know how to read them, those pages tell you everything. The temperature of the air, the chemistry of the water, the plants that grew, the animals that lived and died, the storms that raged and the long silences that followed. The Carnian pluvial episode left its signature in these layers with extraordinary clarity. When geologists Schlager and Schullenberger first examined the northern limestone Alps in the 1970s, what caught their attention was a sudden interruption in the record. For millions of years, the rocks in that region were carbonates, limestones and dolomites that form in warm, dry conditions where there is little runoff from land. And then abruptly, the carbonates stopped and were replaced by a dark, fine-grained siliciclastic layer, the kind of rock that only forms when enormous amounts of sand, silt and clay are washed off the land by heavy rainfall. It was as if someone had drawn a line through the rock record and said, "Here, the world changed." Later, Michael Sims and Alistair Ruffle, two geologists working at the University of Birmingham in England, connected these observations with extinction data from marine fossils. They noticed that the timing of the siliciclastic layer matched a sharp turnover in marine life, a point where many species disappeared and new ones appeared. In 1989, they published their hypothesis. The climate had changed dramatically and globally, and the biological upheaval was a direct consequence, and they named it the Carnian pluvial episode. At the time, their idea was met with skepticism. A global shift to wet conditions lasting 1 million years or more seemed extraordinary, and extraordinary claims need extraordinary evidence. But over the following decades, that evidence accumulated from every corner of the planet. Fossil pollen and spores provided one of the clearest signals. When researchers sifted through sediments from the Carnian, they found that spores from ferns increased dramatically during the CPE, while pollen from drought-tolerant plants declined or vanished entirely. Ferns thrive in wet, humid environments. Their sudden dominance in the fossil record is as clear an indicator of rainfall as a rain gauge. Oxygen isotopes provided another line of evidence. Water molecules contain different isotopes of oxygen, and the ratio between them shifts depending on the temperature and rainfall patterns. By analysing these ratios in carbonate rocks and in the tiny tooth-like fossils of conodonts, scientists reconstructed the temperature curve of the Carnian seas. What they found was a warming event of 4 to 8 degrees Celsius, consistent with a massive injection of greenhouse gases into the atmosphere. Carbon isotopes told a complementary story. During the Carnian, at least 4 sharp negative shifts in carbon isotopes were detected in both marine and terrestrial sediments around the world. Each of these shifts, known as negative carbon isotope excursions, corresponds to a sudden injection of carbon into the atmosphere, exactly what you would expect from a major volcanic eruption. 4 excursions, 4 volcanic pulses, You're perfectly matching the predictions made by researchers studying the Wrangellia eruptions. Mercury, that liquid metal we associate with old thermometers, turned out to be one of the most precise tools for connecting the volcanism to the climate change. Volcanic eruptions release mercury into the atmosphere, and this mercury drifts across the globe before settling into lakes and oceans, where it becomes trapped in sediment. By measuring mercury concentrations in Carnian Age lake deposits from China, researchers found 4 distinct spikes that lined up precisely with the carbon isotope excursions and with the periods of increased rainfall. Each spike was the chemical fingerprint of a Wrangellia eruption, carried halfway around the world by the wind and deposited in the mud of a lake that no longer exists. And what makes this detective work so compelling is that the evidence is not confined to a single location. The same signals, the same pollen shifts, the same isotopic changes, the same mercury spikes appear in rocks from Europe, from China, from North America, from South America. Every continent tells the same story. The rain was not a local event, it was planetary. To stand before one of these exposed rock faces, to run your hand across the boundary between the dry world and the wet world, is to touch the memory of a storm that lasted longer than all of human civilization. The pale carbonate below your fingers was laid down in a world of deserts and dry heat. The dark siliciclastic layer above it was deposited by floods that covered continents, and in that thin transition, and in those few centimetres of stone that represent thousands of years, the entire history of life on Earth changed direction. The rocks cannot speak, of course. They do not have voices, but they do not need them. Every mineral, every trapped bubble of ancient air, every fossilized spore is a word in a story written by the planet itself. And if you listen carefully enough, if you have the patience and the tools and the curiosity, the earth will tell you everything. If you could close your eyes and step into the Carnian world, the first thing you would notice is not what you see but what you hear, or rather, what you can never stop hearing. Imagine a world where silence does not exist, where every single moment, waking or sleeping, is filled with the hammering of rain against leaves, against stone, against water, drop after drop, without pause, without mercy, striking the surface of everything from every direction, creating a wall of sound so constant that your brain would eventually stop trying to process it as individual raindrops and would hear it instead as a single endless roar. Now add the thunder. In our modern world, a thunderstorm is an event. It arrives, it crashes overhead, it passes. Children count the seconds between lightning and thunder, measuring how close the storm is. Dogs hide under beds, the lights flicker, and then it is over and the quiet returns. But in the Carnian world, the thunder never stops. The atmosphere, supercharged with heat and moisture from the Wrangellia eruptions, is so unstable that storms form continuously. Lightning forks across the sky every few minutes, sometimes every few seconds, illuminating the landscape in strobe-like flashes that turn the darkness into a strange flickering twilight. The thunder that follows is not a single clap, but a continuous rolling wave, overlapping with itself, never quite fading before the next bolt adds its voice to the chorus. For the creatures living through this, the noise would have been more than uncomfortable. It would have been disorienting. Modern animals respond to thunderstorms with visible stress. Herds of cattle press together facing away from the wind. Birds fall silent and seek shelter. Even marine mammals in shallow water change their behaviour when thunder rolls overhead. Now imagine that stress sustained not for hours or days, but for years, for decades, for centuries. Generations of animals would be born, live and die without ever hearing quiet, without ever experiencing the simple peace of a still night. Think about what that means for survival. A predator that relies on hearing to locate its prey would be functionally deaf. The rustle of a small animal moving through undergrowth, the splash of a fish breaking the surface of a pond, the crack of a twig under a foot, all of these sounds would be swallowed by the relentless drumming of rain and the rolling booms of thunder. Hunting would become harder, less reliable, more dependent on sight and smell alone. For prey animals, the situation would be equally dire. The ability to hear an approaching predator is one of the most fundamental survival tools in the animal kingdom. In a world where that tool is useless, every moment spent feeding, drinking, or resting would carry an elevated risk. Sleep, too. It would be nearly impossible to sustain. In modern animals, deep sleep requires a sense of safety, a confidence that the world is not actively threatening you. Thunder disrupts that confidence. Every clap would jolt a sleeping animal into wakefulness, flooding its body with stress hormones, wearing down its immune system, reducing its ability to heal, to reproduce, to think clearly. Over generations, this chronic stress would thin populations, making them more vulnerable to disease, to starvation, to predation. The land during the Carnian pluvial episode was not merely wet. It was loud. It was electric. It was a place where the sky itself seemed alive with malice, where the air crackled with energy, and where the ground shook with the combined force of thunder and rushing water. The earth was not still. It was restless, the groaning under the assaults of a storm that would not end. And yet, beneath the surface of the ocean, the same storm was reduced to a distant rumble. Sound travels differently through water than through air. The explosive crack of lightning, so sharp and terrifying on land, would have been muffled and distorted underwater, reaching the ears of marine creatures as a low, distant vibration rather than a startling shock. The rhythmic pounding of rain on the ocean surface, while audible from below, would have been a softer, more diffuse sound. Something closer to white noise than to the sharp assault that land creatures experienced. The ocean once again acted as a buffer. It absorbed the chaos of the surface and translated it into something bearable, another reason that the water was safer than the land. And while the storm raged and the noise pressed down on every living thing, evolution itself was being forced into a sprint. Under normal conditions, evolution is a slow and patient sculptor. Changes accumulate over hundreds of thousands of years, tiny adjustments in body shape, in diet, in behaviour that gradually shift a species from one form to another. But the Carnian pluvial episode was not a normal condition. It was a crisis, a sudden and sustained alteration of the environment so severe that the slow pace of ordinary evolution was not fast enough. What happens to life when the world changes faster than biology can keep up? Some species simply cannot adapt. Their bodies are too specialized, their diets too narrow, their reproductive cycles too slow to respond to a shifting world. These species decline, their populations shrink, and their fossils become rarer in the rock record until eventually they disappear entirely. This is the fate that befell the rhynchosaurs, the dicynodonts, and many families of archosaurs during the Carnian. But for other species, the crisis became a forge. The pressure of the changing environment tested every individual, every generation. Those with traits that happened to suit the new world survived and passed those traits to their offspring. Those without them did not. And because the pressure was so intense, because the difference between survival and extinction was so thin, the pace of evolutionary change accelerated. This is visible in the fossil record. The diversity of dinosaurs, which had been low and static for millions of years before the Carnian, begins to increase noticeably during and immediately after the CPE. New body plans appear, new sizes are reached, new ecological niches are filled. The same is true for crocodilomorphs, for turtles, for lepidosaurs, for mammalia forms. The storm did not just clear the stage of the old players, it forced the new players to innovate at a pace that would have been impossible under stable conditions. In the ocean, the same accelerated evolution was taking place. The groups that survived the marine extinctions of the Carnian did not simply persist in their old forms. They diversified rapidly, filling the niches left by the species that had vanished. New types of ammonoids appeared. New families of fish evolved. The plankton community was revolutionized. by the arrival of Coccolithophores and Dinoflagellates, organisms that would go on to dominate marine food chains for the next 230 million years. And the CPE was not just a disaster, it was an engine of innovation, driving life in new directions at a speed that normal circumstances would never have permitted. There is a strange beauty in this, if you are willing to look for it. In the midst of destruction, in the darkest chapter of the Triassic, life was not merely surviving, it was creating. New forms, new strategies, new ways of being alive were emerging from the wreckage of the old world, as if the storm itself were a sculptor, chipping away the outdated and the rigid to reveal something new and resilient underneath. The rivers of the Carnian world embodied this paradox more than anything else. Before the rains, rivers on Pangaea were modest things, thin channels winding through dry valleys, their banks stable, their courses predictable. But when the rains intensified and the volcanic warmth accelerated the water cycle, those modest streams became something unrecognizable. Rivers swelled until they tore their banks apart. Channels that had been a few meters wide expanded to hundreds of meters, their currents carrying enormous loads of soil, rock, and debris. Valley floors that had been dry for millennia were buried under thick layers of mud and sand, deposited by floods of a scale that modern rivers can barely approach. Whole landscapes were erased in a single season, rewritten by the force of water moving across the surface of a continent that had no defences against it. For the creatures that lived near these rivers, the transformation was lethal. Nesting sites along riverbanks were destroyed overnight. Migration routes that had been followed for generations were blocked by new channels, flooded plains and unstable terrain. Small animals trying to cross swollen rivers were swept away. Large animals, attempting the same crossings, found themselves mired in soft sediment on the far side, trapped in mud that had been solid ground just days before. But the rivers were not only destroyers. Each flood carried nutrients from deep within the continent, minerals washed out of rocks by the acidic rain, depositing them in broad floodplains where new life could take root. The same water that drowned existing forests also spread the seeds of future ones, carrying fern spores and conifer seeds far beyond their original range and depositing them in rich, fertile soil. Without the rivers, the great forests that would eventually cover post-CPE Pangaea might never have spread so quickly or so widely. The rivers also created barriers that shaped evolution in subtle ways. When a river swells to the point where it cannot be crossed, it becomes a wall. Populations of animals that once moved freely across the landscape are suddenly divided, cut off from one another by currents too strong to swim. Over time, these separated populations begin to evolve independently, adapting to their own local conditions, drifting apart genetically until they become distinct species. The Carnian rivers were not just moving water, they were drawing new lines on the map of life, creating boundaries that would shape the distribution of species for millions of years. And the rivers did one more thing that connects to the heart of our story, and they carried the weight of the dying land into the sea. Every flood that surged across Pangaea eventually reached the coast, and when it did, it poured its burden of sediment, minerals, organic matter, and dissolved chemicals into the ocean. This is how the algal blooms were fed, how the coastal waters became choked with nutrients, how the oxygen crashes began. The rivers were the bridge between the nightmare on land and the trials in the sea, carrying the consequences of the storm from one world into the other. Imagine standing at the mouth of one of these Carnian rivers, where the brown sediment-heavy water meets the darker blue of the open ocean. The current pushes outward, staining the sea for miles. Floating logs torn from distant forests drift past like the wreckage of a shipwreck. The water is warm, murky, thick with the dissolved remains of a continent being slowly washed into the sea. Somewhere beneath that murky surface, ichthyosaurs are hunting, adjusting their patterns to the changing water, moving further offshore to find the clearer, more oxygenated waters where their prey can still survive. They are adapting, as they have always adapted, because the ocean gives them time and space to do so. On the bank behind you, the land is a different story. The ground is soft and unreliable. The trees that remain are waterlogged, their roots undermined by constant saturation. A reptile carcass lies half buried in the mud, its ribs exposed, evidence of yet another creature that could not escape the floods in time. The air smells of sulphur and wet earth and decay. The river does not care about any of this. It flows, it carries. It destroys and it nourishes, and it connects the two worlds, land and sea, in a cycle that has been running without interruption since the first rains fell. This is the paradox of the Carnian pluvial episode. Every drop of rain was both a weapon and a gift. Every flood was both an ending and a beginning. Every extinction opened a door that would not have opened otherwise. And the boundary between destruction and creation was not a wall, but a river, carrying the story of one world into the heart of another. There is something haunting about knowing that most of the creatures that lived during the Carnian pluvial episode are gone forever. Not just extinct in the way that we use the word casually, not simply absent from the modern world, but gone in a way that is absolute and irreversible, their bodies decomposed in the mud, and their lineages ended without descendants, and for many of them, not even a fossil remains to prove they existed at all. When we look at the fossils that have survived, we are looking at a tiny fraction of the life that once filled the Triassic world. Paleontologists estimate that for every species preserved in the fossil record, there are hundreds, perhaps thousands, that left no trace whatsoever. Their soft bodies dissolved before they could be buried. Their bones were crushed by the weight of sediment before they could mineralize. Their habitats were washed away by the same floods that might have preserved them in other circumstances. This means that the Carnian world we reconstruct from fossils is like a photograph taken in very low light. We can see the shapes, the outlines, the general composition, but the details, the colours, and the textures, the sounds, the behaviours, the relationships between species are mostly lost. We will never know what the call of a Rhynchosaur sounded like as it moved through a Triassic dawn. We will never see the patterns on the scales of a temnospondyle basking at the edge of a freshwater pool. We will never watch a juvenile ichthyosaur learning to hunt alongside its mother in the warm waters of the Panthalassa Ocean. These are the gaps in the story, the silences that no amount of research can fill. And they are worth sitting with for a moment, because they remind us of how much has been lost, not just in the Carnian, but in every mass extinction that has shaped the history of life on Earth. Every fossil in a museum is a messenger from a vanished world, carrying a fragment of a story that can never be told in full. But the Carnian pluvial episode was not only a story of loss. Within the chaos, within the fire and flood and poisoned rain, there was beauty. Strange, unexpected, overwhelming beauty. Imagine standing on a hillside during a brief break in the rain, looking out over a landscape that has been utterly transformed. Where once there was red desert, there is now a vast expanse of green. Ferns have colonized every available surface, their fronds unfurling in waves that stretch to the horizon. Young conifers are pushing upward, their trunks still slender but their crowns already reaching for the grey sky. Mosses carpet the ground between them, soft and wet, absorbing the constant moisture like sponges. The air is thick with humidity, heavy with the smell of wet earth and resin, and the faint sweetness of new growth. And it is a landscape that is simultaneously terrifying in its strangeness and breathtaking in its vitality. Now imagine a burst of sunlight breaking through the clouds, something that happens rarely in the Carnian world. For a few minutes, golden light pours through a gap in the overcast sky, illuminating the ferns and the standing water in the valleys below. The landscape glows. Dragonflies, their wings as wide as a man's outstretched hand, catch the light as they dart through the humid air, their bodies flashing like shards of glass. The surface of a newly formed lake shimmers, and in its still waters you can see the reflection of the clouds, of the trees, of a world that is rebuilding itself from the wreckage of the old one. In the swamps, life teems with a ferocity that seems almost defiant. Amphibians gather in the shallow waters, their calls rising in a chorus that competes with the distant rumble of thunder. Insects swarm above the surface, their humming creating a living cloud of wings. Small reptiles scurry through the undergrowth, picking their way between fallen logs and dripping ferns, their eyes alert, their bodies lean with the kind of energy that only the hungry and the newly liberated possess. The ecosystem is raw, young, still sorting itself out, but it is alive, intensely and undeniably alive. Even the storms themselves carried a terrible beauty. Imagine looking up at a sky filled with clouds so thick and dark that they seem to have weight, as if they could press down and flatten the land beneath them. Lightning arcs across this canopy in silent branching patterns before the sound catches up, arriving as a deep, rolling wave that shakes the ground. The rain falls in sheets, each drop catching what little light remains, creating a curtain of silver between you and the world beyond. The air crackles with electricity. The horizon flickers with distant strikes, each one illuminating a momentary landscape of rivers and forests and mist before darkness reclaims it. There is a word for the feeling this kind of scene produces. Not fear exactly, though fear is part of it. Not awe, though awe is there too. It is something closer to reverence, a recognition that you are standing in the presence of forces that are beyond your control, beyond your understanding, beyond anything that could be described as merely weather. This was the earth at its most raw, at its most creative and destructive simultaneously, and even in the midst of the nightmare, it was magnificent. And this beauty matters because it is part of the truth. The Carnian pluvial episode was not simply a disaster, it was a transformation, and transformations, however painful, carry within them the seeds of something new. The same rain that drowned the old world watered the new one. The same fires that destroyed the ancient forest cleared the ground for the forest that followed. The same extinctions that erased the rhynchosaurs and cynodonts opened the ecological space for dinosaurs, for mammals, for every creature that would shape the next 230 million years of life on Earth. Try, if you can, to imagine humanity in this world, not because our species existed during the Carnian, because it did not by more than 200 million years, but because the thought experiment is useful for understanding just how extreme the conditions were. We are creatures of stability. Everything about our civilization, our agriculture, our cities, our transportation networks, our economies, is built on the assumption that the weather will behave within certain predictable limits. We plant crops expecting them to receive measured amounts of sunlight and rain. We build houses expecting them to withstand seasonal storms, not eternal ones. We store food in dry spaces, trusting that the air will not be constantly saturated with moisture. We sleep soundly in our beds, trusting that the rain will stop and the sun will return. In the Carnian world, none of those assumptions would hold. Farming would be impossible, because no crop can grow in soil that is permanently waterlogged. Seeds would rot before they could germinate. Grain would mould in storage. Fields would dissolve into mud. And the machinery of modern agriculture, tractors, harvesters, irrigation systems, would be useless against a flood that never recedes. Our buildings would fail. Foundations designed for solid ground would crack as the earth beneath them softened. Roofs engineered for seasonal rainfall would buckle under the weight of rain that never stops. Basements would flood. Electrical systems would short. The infrastructure that we take for granted, the roads, the bridges, the power lines, the internet cables buried underground, would corrode and collapse under the relentless assault of water and acid. Transportation would grind to a halt. Roads would wash away. Airports would flood. Railways would warp on waterlogged ground. The supply chains that move food from farms to cities, that carry medicine to hospitals and fuel to power stations, would fracture within weeks. Communities that rely on those supply chains, which is to say all communities, would find themselves isolated, cut off from the resources they need to survive. And then there is the human body itself. We are warm-blooded creatures who regulate our internal temperature with remarkable precision, but that regulation depends on the ability to dry off, to warm up, to find shelter from the elements. In a world of unending rain, hypothermia would be a constant threat. Skin would break down from prolonged exposure to moisture. Infections would spread rapidly in the damp. Diseases carried by insects, which would thrive in the wet conditions, would ravage populations that no longer had access to medicine or clean water. The thought is sobering. With all of our technology, all of our intelligence, all of the tools that have allowed us to dominate every ecosystem on the planet, we would not last long in the world of the Carnian pluvial episode. The creatures that survived it, the small, adaptable, flexible creatures that weathered 2 million years of rain, possess something that all of our technology cannot replicate. They could change. Their biology allowed them to adapt, generation by generation, to conditions that would have destroyed any fixed way of living. Our buildings cannot evolve. Our roads cannot sprout new roots around floods. Our crops cannot rewrite their genetics to tolerate acid rain. We are, in many ways, the rhynchosaurs of our own age, brilliantly adapted to the world as it is, and potentially helpless if that world changes too quickly. And this brings us to the most remarkable aspect of the dinosaur story during the Carnian pluvial episode. Their rise was not inevitable. It was not destined. It balanced on the thinnest possible edge. If the Wrangell eruptions had been slightly less intense, the rains might not have lasted long enough to collapse the ecosystems that the old rulers depended on. Rhynchosaurs might have weathered a few centuries of wet weather and returned to their former abundance when the dry conditions resumed. Dinosaurs would have remained small, marginal creatures hiding in the shadows, a footnote in the story of the Triassic rather than the headline. If the eruptions had been more intense, the environmental devastation might have been so total that even the adaptable dinosaurs could not have survived. The atmosphere might have become too toxic, when the rains too acidic, the floods too violent for any land animal to endure. Life on land might have been pushed back to the simplest organisms, requiring millions of additional years to rebuild anything resembling a complex ecosystem. But the eruptions were exactly intense enough, and lasted exactly long enough to clear the old world without destroying the capacity for a new one to emerge. The rhynchosaurs disappeared. The Dicynodonts declined. Many archosaur families faltered, and in the spaces they left behind, dinosaurs found room to grow. This was not a triumph of strength, it was a triumph of circumstance. The dinosaurs did not defeat their rivals. The storm did that. What the dinosaurs did was survive the storm, and then when the rain began to slow and the sky began to clear, they were the ones standing in the open and ready to expand into a world that had been emptied of the competition that had held them back for millions of years. Imagine that final phase of the Carnian pluvial episode. The storms are less frequent now. The volcanic pulses that have been driving the rain for nearly 2 million years are finally subsiding. The atmosphere, which has been saturated with CO2 and sulfur, is slowly beginning to stabilize. The mega monsoons that have been hammering Pangaea are weakening, and for the first time in living memory, there are stretches of days, then weeks, when the rain pauses. The landscape that emerges from those pauses is unrecognizable. Where deserts once stretched to the horizon, there are now dense forests of ferns and conifers. Rivers, though still swollen, are beginning to settle into more permanent channels. The lakes that formed during the worst of the floods are stabilizing, their shores ringed with new growth. The air is still damp, still warm, but it no longer carries the oppressive weight of a sky that is perpetually falling. And through these new forests, along the banks of these new rivers, small creatures are moving with increasing confidence. Two-legged dinosaurs, their bodies lean and quick, their lungs efficient, their appetites flexible, are exploring territory that has never been theirs before. They are not yet the towering giants of the Jurassic and Cretaceous periods. That transformation is still millions of years in the future, but they are here, alive, and growing bolder by the generation. The storm gave them their chance. Evolution will do the rest. In the ocean, the parallel story is even more striking. And the marine ecosystems that survived the CPE are not simply recovering. They are being rebuilt from the ground up, with new organisms filling roles that had never existed before. The Scleractinian corals are spreading along shallow coastlines, building reefs that will become the most biodiverse habitats in the sea. Coccolithophores are multiplying in the open water, their tiny calcium carbonate plates drifting down to the seafloor in quantities so vast that they will eventually form the white chalk cliffs that line the coasts of England and France, the foundations of the modern ocean, the ocean that we depend on today for food, for climate regulation, for the very oxygen we breathe, are being laid down in the aftermath of the greatest storm in Earth's history. The land and the sea are healing together, but they will never forget what happened. The scars of the Carnian pluvial episode are written into the DNA of every organism that survived it, encoded in the genetic instructions that told ferns how to grow in waterlogged soil, that told conifers how to resist acid rain, that told dinosaurs how to walk upright through mud, that told ichthyosaurs how to hunt in murky, oxygen-depleted water. Every adaptation that emerged from the storm is a permanent record of the crisis, carried forward through time in the bodies of the survivors and their descendants. And we are among those descendants, not of the dinosaurs, not directly, but of the mammalia forms that diversified during the Carnian tiny insect-eating creatures that survived in burrows and under fallen logs while the world above them fell apart, and their DNA carries the memory of that survival, passed down through 232 million years of unbroken inheritance, all the way to us. When you take a breath tonight, when you feel your lungs fill with oxygen, you are using a respiratory system that was shaped, in part by ancestors who breathed the heavy, CO2-laden air of the Carnian pluvial episode and survived. We are children of the storm, whether we know it or not. There is a moment in every great upheaval when the balance tips, not from destruction toward more destruction, but from destruction toward something else, toward renewal, toward the first and tentative stirrings of a world that is trying to rebuild itself from the wreckage of the old one. In the Carnian pluvial episode, that moment did not arrive on a single day or in a single year. It arrived gradually, like the tide coming in, and so slowly that no creature alive could have noticed it happening. The first sign was the soil. During the worst of the rains, the soil across much of Pangaea had been stripped, washed away by floods that carried it into rivers and eventually into the sea. What remained was thin, acidic, and depleted of the nutrients that plants need to grow. But as the volcanic pulses weakened and the acid rain diminished, the chemistry of the soil began to change. Minerals that had been locked in the bedrock were slowly released by the continuing, if less intense, rainfall. Nitrogen compounds deposited by lightning strikes, which had been relentless during the height of the storms, enriched patches of ground that had been barren. In these enriched patches, life took hold. Mosses came first. They are among the most resilient plants on Earth, capable of surviving in conditions that would kill almost anything else. They need no deep roots, no rich soil, no pollinators. They simply need moisture, and moisture, even as the rains were declining, was still abundant. The mosses spread across exposed rock and thin soil like a living carpet, their green surfaces capturing what nutrients they could from the rain and the air, building the thinnest possible layer of organic matter on top of the bare ground. Behind the mosses came the ferns, as they always did, their spores drifting on the humid wind and settling into any patch of soil that offered even the slightest foothold. And behind the ferns came the conifers, slower but more permanent, their seedlings pushing through the fern canopy to claim the light above. Each generation of plants enriched the soil a little more, adding organic matter when they died, creating a foundation for the generation that followed. It was a cascade of renewal, each step making the next one possible, each layer of life building on the one beneath it. Animals followed the plants, as they always do. Where there are plants, there are insects that feed on them. Where there are insects, there are small predators that feed on the insects. Where there are small predators, there are larger predators that feed on them. The food chains of the post-Carnian world assembled themselves with an efficiency that speaks to the fundamental resilience of life on Earth. Given even the smallest opportunity, the slightest foothold, the barest minimum of resources, life expands to fill whatever space is available. It does not wait for conditions to be perfect. It begins as soon as conditions are possible. The swamps that had formed during the rains did not disappear as the climate dried. Many of them persisted, fed by rivers that had been permanently rerouted by the floods. These swamps became some of the richest ecosystems of the post-Carnian world, supporting dense communities of amphibians, fish, insects and reptiles in a web of interactions that grew more complex with each passing century. The sound of these swamps, the croaking of amphibians, the buzzing of dragonflies, the splash of a phytosaur lunging after prey, replaced the roar of rain as the dominant soundtrack of the Triassic landscape. Life was not just returning, it was making noise again, filling the silence that the storm had left behind. In the oceans, the recovery followed a similar pattern, and the areas that had been hit hardest by anoxia and algal blooms were the first to recover, as the reduction in nutrient runoff from land allowed the water chemistry to stabilize. Oxygen levels rose, clarity improved. And into these recovering waters, marine organisms expanded with the same relentless optimism that characterized the recovery on land. Reefs grew, fish diversified. Plankton populations stabilized into the patterns that would persist, with modifications, for the next 232 million years. The world after the Carnian pluvial episode was not a return to what had been. It was something new. The deserts of old Pangaea did not come back in their full extent. The creatures that had ruled the pre-Carnian world did not reappear. The ecosystems that had been stable for millions of years were gone, replaced by younger, yet more dynamic systems that were still finding their shape. It was a world in transition, balanced between the memory of the storm and the promise of what was to come. And in that transition, in that uncertain, hopeful, still dripping space between catastrophe and renewal, the future of life on Earth was quietly, patiently, irrevocably being decided. When we hear stories about ancient climate catastrophes, it is tempting to treat them as curiosities, fascinating chapters in a book that has nothing to do with us. The Carnian pluvial episode happened 232 million years ago. The creatures that lived through it have been extinct for so long that their bones have turned to stone. The volcanoes that caused it are buried under layers of continental crust that have been shuffled and reshuffled by plate tectonics. It feels distant, alien, disconnected from the world of highways and smartphones and grocery stores that we inhabit. But the truth is less comfortable than that. The forces that drove the Carnian pluvial episode are the same forces that are at work in our atmosphere right now. The chemistry is the same. The physics is the same. The only thing that has changed is the source. During the Carnian, the Rangilaia Large igneous province pumped carbon dioxide into the atmosphere through volcanic eruptions that lasted hundreds of thousands of years. That CO2 trapped heat. The heat increased evaporation. The evaporation drove monsoons. The monsoons became a deluge that lasted for nearly 2 million years. It was a chain reaction, each step triggered by the one before it, each step amplifying the next, until the entire climate system of the planet was knocked off balance. Today we are adding carbon dioxide to the atmosphere through a different mechanism. Instead of volcanic eruptions, we are burning fossil fuels, coal, oil and natural gas that have been locked in the Earth's crust for millions of years. The CO2 that results from this burning is chemically identical to the CO2 that poured out of Rangilaia's volcanic vents. It traps heat in the same way. It acidifies ocean water in the same way. It intensifies the water cycle in the same way. The molecules do not care whether they came from a volcano or a tailpipe. They behave according to the same laws of physics that governed the Carnian atmosphere, and those laws have not changed in 232 million years. The scale is different, of course. The Rangilaia eruptions released their CO2 over a span of 1.6 million years, a Modern industrial emissions have released a comparable impact on the carbon cycle in just 2 centuries. Research published in Nature Communications in 2025 estimated that the onset of the Carnian pluvial episode took roughly 15,800 years to unfold as the atmospheric chemistry shifted from a dry equilibrium to a wet one. We are making similar shifts to our atmosphere in decades rather than millennia. In geological terms, we are moving faster than the volcanoes did. The parallels are not abstract. They are measurable, observable, and increasingly felt. Global temperatures have risen by approximately 1.2 degrees Celsius since the beginning of the industrial era. That is a fraction of the 4 to 8 degree warming that characterized the Carnian pluvial episode, but the trajectory is the same. Storms are intensifying, and the amount of moisture in the atmosphere has increased as warming oceans evaporate faster, and that extra moisture is falling as heavier, more destructive rainfall. Cities that were designed for seasonal weather are flooding with increasing frequency. Agricultural regions that depend on predictable rainfall patterns are experiencing droughts and deluges in unpredictable alternation. In the oceans, the echoes are even clearer. Ocean acidification, driven by the absorption of CO2 from the atmosphere, is dissolving the calcium carbonate structures of corals and shellfish in a process that mirrors almost exactly what happened to marine organisms during the Carnian. Coral reefs, the same scleractinian reefs that were born during the CPE and have flourished for 232 million years, are bleaching and dying under the stress of warming and acidifying water. The foundation of the modern ocean, the very ecosystem that emerged from the Carnian storms as a triumph of resilience, is now under threat from the same chemical forces that created it. There is something deeply disquieting about this symmetry. The event that gave birth to the modern ocean may also contain the blueprint for its destruction. The same CO2 that triggered the transformation of Triassic seas into the modern marine world is now, in a different concentration and from a different source, threatening to undo that transformation. The Carnian pluvial episode teaches us something important about thresholds. For millions of years before the rains began, the climate of Pangaea had been stable. The deserts were hot, the seasons were predictable, and the ecosystems were balanced. Nothing about that stability suggested that it was fragile. Nothing about the clear skies and dry riverbeds warned that they were one volcanic pulse away from a 2 million year storm. The system looked permanent. It was not. Climate systems have tipping points, boundaries beyond which small additional changes produce enormous, often irreversible, consequences. The Wrangellia eruptions pushed the Triassic climate past such a tipping point. The additional CO2 was enough to trigger a cascade of effects: warming, evaporation, monsoon intensification that fed on each other in a self-reinforcing loop. Once that loop was established, it ran for nearly 2 million years before the volcanic output decreased enough for the system to find a new equilibrium. Modern climate science has identified similar tipping points in our own climate system. The melting of polar ice sheets, the release of methane from thawing permafrost, the slowdown of ocean circulation patterns. Each of these has the potential to trigger cascading effects that would be difficult or impossible to reverse on any human timescale. We do not know exactly where these tipping points lie. We do not know how much additional CO2 is needed to push us past them. But we know they exist, because the geological record shows us what happens when they are crossed. The rocks that hold the memory of the Carnian pluvial episode are not just scientific curiosities. They are warnings, written in the language of stone by a planet that has been through this before. But the story does not end with warning. It also ends with something that might, on a quiet night like this, feel a little like hope. The Carnian pluvial episode killed as many as 50% of all species on Earth. It drowned forests and poisoned seas and turned the land into a place where only the most adaptable could survive. But life did survive. And not only did it survive, it emerged from the crisis more diverse, more resilient and more creative than it had been before. The modern ocean was born from those storms. Dinosaurs rose to rule the land for 160 million years. Mammals, including our own distant ancestors, found their foothold. Coral reefs, calcareous plankton, modern conifers, turtles, lizards, crocodilians, all trace their diversification to this period. The storm that seemed like an ending was, in fact, a beginning. This is what the rocks whisper if you listen carefully enough. Not just that the earth can be broken by its own chemistry, but that life, given time, can heal the break. Not by returning to what was, but by becoming something new. Something that carries the memory of the crisis in its DNA, in its behavior, in the very structures of its body, and uses that memory to build a world that is more adaptable, more varied, and more prepared for whatever comes next. Even now, even in us, that memory persists. The tiny mammalia forms that survived the Carnian pluvial episode pass their genetic inheritance down through an unbroken chain of reproduction that stretches 232 million years into the present. Every adaptation they made to cope with the heavy air, the flooded burrows, the unpredictable food supply is encoded somewhere in the deep architecture of our biology. We are the inheritors of their survival, and we carry their lessons in our cells even if we have forgotten them in our minds. DNA is a remarkable thing. It is both a blueprint and a diary, carrying instructions for building a living body while also recording, in its structure, the history of every challenge that body's ancestors ever faced. The genes that tell your lungs how to extract oxygen were shaped in part by ancestors who breathed in an atmosphere thick with volcanic CO2. The genes that regulate your body's response to stress were forged in environments where stress was not an occasional visitor, but a permanent condition. The genes that control your sleep cycles, your immune function, your ability to adapt to changing conditions, all of them carry faint but real echoes of the Carnian, because the creatures that did not possess those adaptations did not survive to pass their genes along. This is the deepest legacy of the Carnian pluvial episode. Not the fossils in the rock or the chemical signatures in the stone, but the living, breathing, reproducing legacy that exists in every organism on Earth today. The storm is written into us. It is written into the ferns that grow in your garden, into the conifers that line mountain ridges, into the crocodiles that bask on riverbanks, into the plankton that drift in every ocean. Every living thing on this planet is a descendant of something that survived the 2 million years of rain, and every living thing carries, in its most intimate chemistry, the proof of that survival. When you close your eyes tonight and feel yourself drifting towards sleep, I know that the body you inhabit is the product of 232 million years of unbroken resilience. Every breath you take is a testament to ancestors who endured conditions that would break our civilization in weeks. Every heartbeat is a rhythm that has been passed down through more generations than any number can meaningfully convey. The Carnian pluvial episode was a catastrophe, but it was also a crucible, and the life that emerged from it, tempered and transformed, is the life that eventually became us. The past is not just history, it is inheritance, and the storms that shaped it are still echoing, faintly but unmistakably, in the body you are resting in right now. There is a thought that returns, gently but persistently, when you spend enough time with this story. It is not a dramatic thought. It does not arrive with thunder or lightning. It settles quietly, like rain on still water. The thought is this: the earth does not need our permission to change. We live our lives as if the systems that support us, the climate, the oceans, the soil, the air, are permanent fixtures, as unchangeable as the laws of physics. But they are not. They are processes, dynamic and responsive, and they can shift from one state to another with a speed that geology measures in the thousands of years, and that human experience measures in lifetimes. The creatures of the Carnian did not see the change coming. They could not have. They lived in a world that had been stable for as long as any of them could know, and they had no reason to suspect that stability was anything other than permanent. We have a reason. We have the rocks, we have the fossils, and we have the isotopes and the mercury spikes and the pollen records and the black shales. We have the entire painstakingly assembled evidence of what happens when too much carbon dioxide enters the atmosphere too quickly. We have the story, written in stone, of a world that changed so fast that most of its inhabitants could not keep up. And we have something else that the creatures of the Carnian did not have. We have the ability to choose. The volcanoes that drove the Carnian pluvial episode could not decide to stop erupting. The CO2 that poured from their vents could not be filtered or captured or redirected. The rain that fell for 2 million years could not be voted on or legislated against. It happened because the physics of the earth demanded it, and nothing alive at the time had any say in the matter. We are different. We understand the chemistry. We can measure the CO2 in the atmosphere to the parts per million. We can model the consequences of different emission scenarios with increasing precision. We have the science to see the tipping points before we reach them, and we have the technology to change course before we cross them. Whether we will use that understanding and that technology in time is a question that the future will answer. But the option exists, and that is something no creature of the Carnian ever had. The rocks are patient. They have been holding their story for 232 million years, and they will hold it for 232 million more. But the warning they carry is not patient. It is urgent, and it is addressed to us, to the only species in the history of this planet that can read it and understand what it means. And the sky does not care whether we listen. But the rocks are speaking, and tonight as you drift towards sleep, their voices are part of the quiet that surrounds you, murmuring of rain that fell before any human ear existed to hear it, and whispering that the earth remembers what we might prefer to forget. When the skies finally began to clear, it was not with a sudden burst of sunlight or a dramatic parting of clouds. It was slow, uncertain, almost hesitant, as if the atmosphere itself was not sure whether the storm was truly over or merely pausing. The volcanic pulses from Rangelia, which had been driving the entire climate disruption, were finally subsiding. The magma plume deep beneath the Panthalassa Ocean was cooling, losing its energy, releasing less gas with each passing century, and the 4 great waves of eruption that had lasted for the 1.6 million years were coming to an end, not with a bang but with a gradual, almost imperceptible fading. At first the change was visible only in the rock record. The siliciclastic sediments that had dominated the Carnian, those dark wet layers of mud and silt that spoke of endless rainfall, began to give way to lighter, drier deposits. Carbonate platforms, the great limestone structures that form in warm, clear, shallow seas, started to re-establish themselves in regions where they had been buried under sediment for hundreds of thousands of years. The chemistry of the atmosphere began to shift as the excess CO2 was slowly absorbed by the expanding forests and the recovering oceans, drawn out of the air molecule by molecule, year by year, and locked away in wood and stone. On the land, the change was felt as a thinning of the clouds, not every day, not even every week, but gradually, over the course of centuries, the perpetual overcast began to develop breaks. Gaps appeared in the grey canopy, and through those gaps sunlight, real, direct, unfiltered sunlight, touched the ground for the first time in living memory. Imagine what that must have been like for a creature that had never seen it. Every animal alive at that point had been born under grey skies. Every plant had grown in diffused, filtered light, the warmth of direct sun on the back of a small reptile, the sharp-edged shadows cast by trees that had only ever known the soft blur of overcast light. These would have been new sensations in a world that was slowly, tentatively, remembering what it felt like to be dry. And the forests that had grown during the rains did not disappear. They were too well established, their roots too deep, their canopies too wide, but they changed. The ferns that had been the first colonizers of the wet world began to give way, in many regions, to the conifers that had been growing behind them. These conifers were taller, stronger, better adapted to the slightly drier conditions that were beginning to return. Their needles shed water efficiently, and their deep root systems could survive both the remaining wet episodes and the drier intervals between them. The forests of the post-Carnian world were not the same as the forests that had existed before the rains. They were new, composed of new species shaped by the memory of the storm, and they would form the foundation of ecosystems that lasted for millions of years, and the swamps began to stabilize. Many of the vast shallow lakes that had formed during the worst of the flooding either drained or settled into permanent bodies of water with defined shorelines and balanced ecosystems. Wetlands remained, but they were no longer the anarchic, ever-expanding swamps of the CPE. They were settled, productive environments where amphibians, fish, and semi-aquatic reptiles could thrive without the constant threat of flash floods or sudden changes in water level. The rivers narrowed. The torrential flows that had carved new channels across Pangaea's surface slowed, constrained by decreasing rainfall and the stabilizing effect of the new forests, whose roots bound the soil and prevented the kind of catastrophic erosion that had characterized the Carnian. The rivers remained, because they had been permanently reshaped by the floods, but they became predictable, their courses settled, their banks lined with vegetation. And through all of this, the creatures that had survived the storm were stepping into their inheritance. Dinosaurs, still small by the standards of their later glory, but growing bolder and more diverse with each generation, spread across the recovering landscape. They had spent the last 2 million years learning to survive in chaos. Now, as the chaos faded, they found themselves in a world that was remarkably well suited to their talents. The upright posture that had kept them above the mud now gave them speed and endurance on firmer ground, and the flexible diets that had sustained them through the food chain disruptions of the CPE now allowed them to exploit the new plant communities and the new insect populations that were flourishing in the post-storm world. The efficient lungs that had helped them breathe in a CO2-heavy atmosphere now gave them a stamina advantage over rivals whose respiratory systems were less advanced. They were not yet the colossal sauropods that would shake the earth with every step. They were not yet the towering tyrannosaurs that would terrify every creature within miles. Those transformations were still tens of millions of years in the future, but the foundation had been laid. The ecological space had been cleared. The traits that would carry them to dominance had been forged in the crucible of the storm. From this point forward, dinosaurs would only grow in size, in diversity, and in their grip on every terrestrial ecosystem on the planet. Their reign, the longest of any major animal group in Earth's history, was about to begin. In the ocean, the story reached a similar resolution. The marine ecosystems that had been stressed but not broken by the CPE were recovering with remarkable speed. The scleractinian corals, those newcomers that had appeared during the storm, were building reefs that were larger, more complex and more biodiverse than anything that had existed before. These reefs would become the rainforests of the sea, supporting thousands of species in intricate webs of interdependence that would persist for the next 232 million years. The coccolithophores, those tiny plankton that had first appeared during the Carnian and were multiplying across the open ocean. When they died, their calcium carbonate shells drifted down to the seabed in a gentle, continuous snow of white particles. Over millions of years, those particles would compress into chalk, forming the great chalk deposits that underlie much of Europe and North America. The white cliffs of Dover, that iconic stretch of English coastline, are built from the accumulated shells of organisms that first evolved during the Carnian pluvial episode. Every grain of that chalk is a tiny monument to the storm. Ichthyosaurs continued to patrol the depths, their streamlined bodies cutting through water that was slowly clearing as the sediment input from land decreased. Some lineages would continue to grow, reaching sizes that rivaled the largest whales. Others would diversify into new ecological roles and becoming specialized hunters of fish or squid or other marine reptiles. The ocean had been their refuge during the storm, and now that the storm was passing, they were positioned to dominate their world for millions of years to come. The Carnian pluvial episode was over. The rain had stopped, the sky was clearing, and the world that emerged from the storm was fundamentally, irreversibly different from the one that had existed before. This is the moment to step back and see the full picture of what we have travelled through tonight. A world locked in drought, stable and predictable, ruled by creatures that had been perfecting their place in it for millions of years. A volcanic eruption of almost inconceivable scale, pouring CO2 into an atmosphere that could not absorb it. A chain reaction of warming, evaporation, and rainfall that turned a desert continent into a marshland. On the surface, a catastrophe. The collapse of ecosystems, the extinction of dominant species, the flooding of habitats that had been stable for longer than any living thing could remember. Beneath the waves, a different story. A story of relative stability, of marine reptiles reaching their peak, of new organisms appearing that would become the foundation of the modern ocean. And then slowly, the clearing of the sky and the emergence of a new world, dominated by new creatures shaped by new plants, built on the lessons that only a crisis can teach. The central truth of tonight's story is this. During the Carnian pluvial episode, the ocean was safer than the land. Not safe in an absolute sense, because the ocean suffered its own losses, its own extinctions, and its own moments of crisis, but safer. The water buffered the temperature swings that devastated land ecosystems. It diluted the toxins that poisoned terrestrial habitats. It maintained food chains that allowed its inhabitants to continue eating, hunting, and reproducing while the land's food chains collapsed. And it gave its creatures time, the most precious commodity in any crisis. Time to adapt, time to adjust, time to wait for the storm to pass. The land offered no such luxury. On land the change was immediate, overwhelming and relentless. Creatures that could not adapt quickly enough were swept away. Ecosystems that had taken millions of years to build were destroyed in centuries. The ground itself, the most fundamental of certainties, became unreliable, soft, waterlogged, shifting, a surface that could no longer be trusted. And so the ocean carried life forward. It was the ark that no one built, the shelter that no one planned, the refuge that existed simply because water, by its nature, absorbs and distributes and stabilizes in ways that air and soil cannot. The creatures that survived the Carnian pluvial episode owed their survival, in large part, to the patient, steady, enduring nature of the sea. Tonight, that sea still exists. It has changed, of course, in ways that would be unrecognizable to a Carnian ichthyosaur. The continents have drifted apart. The single Panthalassa ocean has been divided into the Pacific, the Atlantic, the Indian, the Arctic. The creatures that swim in it are different, the products of 232 million years of additional evolution, shaped by additional crises, additional opportunities, additional transformations. But the fundamental character of the ocean, its depth, its steadiness, its capacity to absorb and endure remains. It is still the great stabilizer of the Earth's climate. It still absorbs heat and distributes it across the globe. It still feeds billions of people. It still produces half the oxygen we breathe. And it still carries, in its chemistry and its biology, the memory of the Carnian storm. The corals on the Great Barrier Reef are the descendants of the first scleractinian reefs that formed during the CPE. The plankton drifting in the North Atlantic are the heirs of the coccolithophores and dinoflagellates that first appeared in those ancient stressed waters. Every marine food chain on Earth today traces its structure back to the reorganization that occurred during and after the Carnian pluvial episode. The modern ocean is, in a very real sense, the child of the storm. So tonight, as you lie here in the quiet, letting the tension drain from your body, letting the thoughts of the day dissolve into the background, know that you are resting in a world that was shaped by 2 million years of rain. The air you are breathing was oxygenated by organisms born from that crisis. The climate that makes your sleep comfortable tonight is regulated by an ocean that learned its current patterns during the Carnian. The very capacity of life to endure and adapt, the quality that allows you to exist at all, was tested and proven during a storm that makes every hurricane and every flood in human memory look like a gentle afternoon shower. The storm is over now. It ended 232 million years ago, and the world that it left behind has had all that time to heal, to grow, to diversify into the extraordinary tapestry of life that we share the planet with today. The rhynchosaurs are gone. The giant semnospondyls are gone. The phytosaurs and the dicynodonts are gone. But their story is not lost. It is written in the rocks, in the chemistry of ancient sediments, in the patterns of fossilized pollen, and in the silent testimony of bones turned to stone. And the survivors, the small, the adaptable, the flexible, their story is written in something even more enduring than rock. It is written in the living bodies of every creature on Earth, in the DNA that has been passed down, generation after unbroken generation, for 232 million years, all the way to this moment, all the way to you. Now let your breathing slow. Let the image of ancient rain fade into something softer, and something more like the sound of a river far away, gentle and steady and sure. The storm is long over. The sky is clear. The forests have grown back taller and greener than before. The ocean is calm, its surface reflecting the light of a sun that has been shining uninterrupted for longer than any storm could last. Let go of the day. Let go of the worry and the noise and the busyness that fills the waking hours. You are safe. You are warm. You are wrapped in the quiet of a world that has weathered the worst that nature could offer and come through the other side changed but alive, always alive. If you found comfort in this journey tonight, a gentle like or a subscribe helps other curious, sleepy minds find their way to this quiet corner. Let me know in the comments where you are listening from and what time it is there. I love seeing how far across the world these soft explorations travel. But for now, rest. The storm is over. The water is still. And the oldest, deepest lesson of the Carnian pluvial episode, that life endures, that life adapts, that life finds a way through even the longest night, is a truth you can carry into your sleep. Good night, friends. The sky is clear. And in the silence that follows the longest storm, there is peace.